stability of carbanion, that is part 3 of Carbanion chemistry. So there are some factors that are responsible for stability of carbanions. Inductive effect. Now here we have to see in which case minus I effect is present, because carbon is carrying negative charge. So minus I effect containing group, if it is present, it will stabilize the carbanion. Then we have hybridization of the charge bearing atom depending on the carbon, that is the negative charge bearing carbon, whether it is double bonded, triple bonded, single bonded. Depending on that, we can have different types of hybridization, sp, sp2, sp3, and hybridization related discussion I have done in the previous part, which is part 2. So please check this video, and the playlist link of Carbanion chemistry that you will get in the description box. You can check it there. So this is the second point for stability of carbanions. Then extent of conjugation of the anion. So if the negative charge on carbon, if it is taking part in some conjugation, that is not possible always. There must be some CC double bond or C double bond O. So that is also another factor for stability of carbon. Aromaticity, very important. So if after the negative charge generation, if the molecule is satisfying the rule of aromaticity, that is if the carbanion is aromatic, that is also the reason for its stability. And the last factor, d orbital effect. Now that is also a type of conjugation, but sometimes there may be some atoms adjacent to the carbanion which is having vacant d orbital, and that is presence of d orbital must be there, so that d pi p pi conjugation is possible. So all these factors we will discuss one by one in detail. Electron releasing group, that is plus I, if this type of groups are attached to carbanion, obviously it will lead to destabilization. But if it is minus I effect, then it will lead to stabilization. So here we have this example, that is methyl carbanion CH3 minus, then we have this 1 degree carbanion where we have one methyl group, as if this hydrogen is replaced by one methyl group, and that will have plus I effect. Now in the next example, 2 degree, where another hydrogen is also replaced by CH3. So now we will have 2 plus I effect containing group, and in the last one all the hydrogens are replaced by 3 methyl groups total. So there will be plus I effect coming from 3 positions. So that is why this is the most unstable. So here you can see this is maximum, then gradually as we move from left to right, stability is decreasing. Now instead of CH3 group, that is plus I contain effect, if we have minus I effect type of group, then how that stability order will be? See, again methyl group we have taken, that is CH3 minus carbanion we have taken, but instead of CH3, now if you replace hydrogen with chlorine which is having minus I effect, it is electronegative. So now stability will increase. So in the third one another chlorine, and in the last one 3 chlorine. So this is CCl3 minus. So here stability as we are moving left to right, it is basically increasing because it is minus I effect. Fine. Another example, here we have this carbon, this is basically CH2 minus. So here plus I effect is coming from these two sides. And in the next example, here we have one hydrogen and 2 CC bond. So plus I effect is coming, sorry, in the previous one it is not, I have written it correctly. Basically here 2 hydrogens are there. So plus I effect is coming only from one side. Fine. In this case it is coming from 2 sides, and the last case it is coming from 3, because there are total 3 CC bonds. So in this case maximum stability will be the first one, then second, and the last one, that is among these 3, that is the least stable. Next we have electronegative group like oxygen just adjacent to this negative charge, and gradually this distance between oxygen and this C minus, it is gradually increasing. Now with distance, this inductive effect, its effect decreases. So that is why, as it is most close in the first example, so that is why here this oxygen, because of its electronegativity, it can stabilize it maximum. So this will be more stable, and as the distance is increasing, now there are 2 carbon present between this negative charge containing carbon and oxygen. So gradually with distance, this minus I effect, that factor will decrease. So that is why stability, as you are moving towards right hand side, that will also decrease. So this is the order. For total 4 examples we have seen under inductive effect. Next, hybridization of the charge bearing atom, that is the negative charge bearing atom. Stability of anion will depend upon the S character of carbanion, because as the percentage of S character is increasing, for sp it is 50%, sp2 it is 33, sp3 it is 25%. So obviously with increase in S character, stability will also increase. So when it is sp hybridized, that is Cc triple bonded, and this carbon is carrying the negative charge, maximum S character, so that is why it is more stable than the next one, because in the second one the carbon, there is a double bond, Cc double bond and one hydrogen. So this carbon is sp2 and this carbon is basically carrying the negative charge, and Ar minus, that means here negative charge will be directly on this carbon. So it may be benzene ring or there may be any group present, but it is sp2. So that is why these two are more or less same. And the last one, here we have sp3 hybridized carbon, which is carrying the negative charge. Basically it is not on hydrogen, it is on carbon. So that is the least stable here. So with decrease in S character, stability is also decreasing. Extent of conjugation of the anion. Now this is most common stabilizing factor. When negative charge, it is in conjugation with a multiple bond like C double bond C, it may be C triple bond C, that is cyano group, then carbonyl NO2, then S star CO2 ET, that is also basically containing carbonyl. So this type of groups, if it is present, conjugation possible. Here we have Cc double bond adjacent to the carbanion. So this type of conjugation. So after conjugation, see, now the negative charge is here. So the negative charge is delocalized. More is the delocalization, more is the stability. Here we have this benzyl carbanion. Here also this can take part with the that is with the Cc double bonds, all the 3 Cc double bonds present in the benzene ring. So we can get many resonance structures like this. If it is carbonyl group, that is negative charge, adjacent to it there is a carbonyl group, then also conjugation possible, that is delocalization of negative charge. Now instead of CO, you can also have H double bond O, though that is not so common like C double bond O, but still it is a same type of effect you can observe here. Then C triple bond N, if it is present, now in the resonance structure we are having Cc double bond and negative charge will be over nitrogen. Then we have NO2 group. So if NO2 group is present, nitrogen is already positive charge and one of this oxygen, any of this oxygen will be negative. So this negative charge, it can make a double bond with this nitrogen. So, and as a result, now the negative charge over this oxygen. Okay. So these are the different examples where conjugation of the anion is negative charge is possible. That means it is now delocalized, and that is the reason for stability. The fourth point, aromaticity. When the conjugation of carbanion is part of aromaticity, now obviously it will be stable. So here we have this very common example. Now what are the factors that are responsible for aromaticity, how to decide it? Related to this I have made a video. Please click on the link appearing on the screen right now. Aromaticity. So the factors for aromaticity, in short I am saying it should be cyclic, there should be planarity should be present, conjugation, and it should follow this 4n plus 2 number of pi electrons. So in this case we have total 6 pi electrons. Now it is matching with this format where n value is 1. So if you put n value 1, it will be total 6 pi electrons. So this carbanion is aromatic in nature, so that is why it is very stable. Now here we have cyclooctatetraene. This is anti-aromatic. It is following these 4n pi rules, and but it is anti-aromatic. It is highly unstable. But when we are adding to Na, 2 electrons will be added to it. Now when 2 electrons are added to it, now it is cyclooctatetra enyl anion. So 2 electrons more. So in this case total 8 pi electrons, where n value is 2. 4 into 2, 8 pi electrons. But in this case, it is total 10 pi electrons because 2 electrons are added, 8 plus 2. Now it is following 4n plus 2 where n value is 2. Okay. So after 2 electron addition, it is becoming anion and now it is aromatic. So this will be stable carbanion. D orbital effect. So this is also a type of conjugation, but instead of p pi conjugation, now it is p pi d pi conjugation. When it is possible, suppose you have this type of groups RSO2, R3p plus substituents. They can lead to stability by accommodating the negative charge of carbanion. Where accommodating? In the d orbital. So here we have this example. This is carbanion, adjacent to it we have RSO2 group. So this RSO2 group, this negative charge, now it is making SC double bond. One of the S double bond O, now it is broken and oxygen is carrying this negative charge. And if we have R3p type of R3p plus, basically this type of group, now this negative charge and positive charge, they are making this double bond. So negative charge is basically accommodated in the d orbital of phosphorus. So these are the 5 factors that are responsible for the stability of carbanions. Now one question may arise that how do we know which factor is most important while deciding the order of stability of carbanion? Suppose 3 to 4 carbanions are given. Mostly this type of questions are very common in different examinations. So when we decide the stability of carbanion for 3 to 4 species, what happens? In some cases you can do it by giving more importance to conjugation, because conjugation factor is very important, and aromaticity. So among these 5, these 2 factors, if it is present, then obviously you have to give priority to them, because it may happen that in some example you have aromaticity, conjugation, in some example you have inductive effect. Give priority to aromaticity and conjugation. But sometimes what happens, it is not so simple. Sometimes these factors can interact with each other in unpredictable ways. Suppose 3 to 4 factors are present together and it becomes difficult to decide that what should be the exact order of stability of carbon. So in those cases, there is actually some solution, but I will discuss that in the next video. Please check that also. So that's all we have in this. If you find it helpful, please like, share and subscribe. I'll meet you in the next video and thank you for your time.